Hello, everybody. So, for those that weren't here yesterday, my name is Margarida, and you'll see where I'm in Faria. And of course, I'll be talking about implementing the lazy theta star algorithm over octree data structure. So, as we all know, this is a marine Marie Sklodowska-Curie endorsed event. And I am staying more specifically in the south of Spain at CATEC, which is a semi-public institution with the support of the University of Seville. So just kind of a motivation, it's a little bit how I met your mother kind of explanation, so it's a little bit long, but I'll get to the point. Why am I doing this? So the point is to create, to advance the tools that we have to inspect very large structures. We already have a lot of research on tabletops and buildings smaller scale, but to really go autonomous with a very large scale, with large volumes and unknown environment. So the idea was to, at the end, would have just the user have to input like a geofence, the boundaries, and also to tell what kind of data he wants to collect with the UAV. And then the UAV would autonomously figure out which points he needs to visit so that at the end he has all this data for the user. This can be any kind of structures. I first shown the industry level, but also obviously this can be very important in natural disaster situations. Right here we have an example of a 3D reconstruction after an earthquake in 2016, where we can see that the damages, and this will enable the other crews to know and to plan what to do in this critical time. And also any other thing, you can have archaeology and also industry. So the big picture of what I have done so far and where this goes in. So I have looked at the data structures and how to store all this information, because we are talking about a very large area, and this has implications on what resources are available in a UAV. We don't have servers or any kind of even the cloud is not available in a marine environment. So first I look at the data storage, then how to, in a big scale, choose which points to visit, and then how to get there in a safe way. First I will start with bottom up, so data storage. So for the data we need something that doesn't take a lot of space, that has a high access speed, and so the organization will be key to making this data available fast. I looked at different options, so sampling, which is not technically a data structure, but also achieves these goals. Also because I am taking the sensors that in whichever way can give me a point cloud. So that I am really focusing my study on 3D reconstruction with point clouds. So one option is, another option is to, from the point cloud, create a surface. This has some issues because the order of the points that you give can create different surfaces, so you can never know exactly what is reconstructed, but has a nice organization to it. Another option is to just separate the space as a grid, as a regular grid. It's a very old approach, which, because of its simplicity, can work good in many situations, but here the problems of the size and the scale that we are working with really don't cut it. So then I came to the sparse grid. We have different backgrounds, so just so I know, who has absolutely no idea what I'm talking about when I say a sparse grid? Okay, everybody else, no. Don't be shy, I want to know. Okay, okay, cool. So this is just the same thing as separating in the same space, but taking into account the data that is inside. So you put together cells that have the same value, let's say. So here would be free, and all of this is free, okay? So then there are no well-known options for this. Like the PCL library is quite popular. More recent approach is the Octomap, and this is what I went for. Because although the PCL is really looked into streaming and to compress these point clouds to then do some more processing. I know that usually in these talks people don't go to this level of detail, but I found that it is really important because the choices that you do at this level really impact the outcome of research and at the end your conclusions. So I actually moved on from the PCL because the Octomap is focused on exploration. And so it enables me to have a grid that has 3 states, which is unknown, free, and occupied. And really also know about the data issue, space issue. So it's really, really tiny, the data footprint that they have, which I will explain the consequences of this later on, but so far this is a good thing. Okay, and obviously it is organized spatially. And one good thing that I want to point out is that the actual, for the processing online, the point clouds themselves for this tree are actually thrown away. They are integrated into the grid and totally thrown away, which is the opposite of what we have in PCL, the classical implementation anyway. Yeah, so now moving on to how do we figure out where we want to go. So I went with this concept of frontier cells. So this is to find points where we have new information, well, they are unknown, right? So basically what we want is to go somewhere which is free so we don't collide with anything, but their neighbors are unknown. And this is what we have exactly here. A frontier point is a known place that is free with unknown neighbors. So this is like some of the preliminary results that I have. It's kind of a weird image. I will see what I mean with this. So here, this all black part is all unknown, and the green part is all free. If there were obstacles, they would be in yellow, but there aren't any. So, and these little white dots, these are the frontiers. And here we have what we will have in a regular grid, but in a 2D. This is all 2D, because it's easier to start with 2D, and then we will move on to 3D. All right, so here you can see that we have like this outline, kind of this white outline surrounding everything. I didn't use the diagonal cells, so this is why I have only 4 here. And then we move on to the sparse grid, and this is the exactly same place, but we can see this dotted line instead of a full-on line. So what we have here is that this is actually a larger cell, and this is just the center of the cell. Okay, so we can see that the same frontiers are identified, but also there are some parts here that the line is somehow larger. So this is because here it's in 3D. So the unknown neighbors that are above and below are also taken into account. And the reason I'm going in depth with this is that I want you to make like a mental drawing class right now. So I really want you to try to picture in your mind what it would look like and where would you need to search if you wanted to get this information. Yes?
Basically, the previous comparison was about the standard grid has some scale and some precision rate, but the scaling grid which you are using can have multiple and bigger cells which can cover the common areas in one data node, and therefore it's more effective for the representation, and you can have bigger precision because you can use smaller cells to cover the areas.
Yes, except for one detail is that the precision is not necessarily different because you can set the precision with which is the highest resolution that you want to go in a regular grid, okay? It's just how fast. Yes, that part, yeah, totally, yeah. Yeah, exactly. So I have at least one listener, that's good. I'm going to tell you that here in this image, everything that is unknown is see-through, all right? So I want to ask if anybody can figure out how many frontiers do we have in this particular image. What do you mean? No, there is no observation point. It's like, this is the space that you have. This is the space, really sampled down space of what you are investigating. And this is the information that you have in your sparse grid. So the unknown points are transparent, like here, 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 here. And the known points are in white. And the obstacles are in black. So knowing this, and knowing that the frontier point is known, free, and have unknown neighbors, how many frontier cells do we have right here? Very well. Okay, so I'm trying to really make you think about this in a 3D way. So I want you to notice that what I'm saying here, I have unknown neighbors, okay, but I am here. This guy has very different neighbors. It's like this multicultural ethnicity of neighbors, right? Because we have these big guys, we have these little guys, we have occupied. So one big key point will be you have to figure out a way first to know which is your size, and then what is the size of your neighbor, okay? And this will show up later on. Because neighbors can be, if you're bigger, then what I did was to assume that all my neighbors are small, and then so that I know what would be the center of a small neighbor, then I have the option to check if this is in fact a small or you have like a bigger one, and to just then we have something like this. So this would be like the first thing that it assumes is that everything is the minimal resolution. Then it goes to check what is in fact the resolution. Then this is like the neighbors that we have. Okay? So this is going from 2D. Now we're speaking in 3D. All right, guys? Okay. So this is one key aspect obviously for frontier cells. But I am explaining this to you because this is also a key aspect in implementing the lazy theta star, as we'll see further on. So remember when I mentioned about the really small data footprint? The thing is with the Octomap is that each node only knows about his identification within one layer and the pointer to where the information of his children are, okay? So we need to work with this minimum, very bare bones information of each node to figure out everything we need to figure out about the world. And so then to figure out the neighbors, as I told you, you have to figure out what is your size. And for this, you have to go through all the nodes from the mother, let's say, which would be all of this. And then to go for the smaller ones would be this, 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 and this, and this. And then go all the way to the tiny node that you're looking for, whichever size heat may be. Okay. Now for the really lazy theta star focused part, which is how I figure out how to make a waypoint sequence that goes from where the UAV is to where my frontier cell is without hitting anything, hopefully. Okay. So for this algorithm, we will need random access to the data. We will need to know the cell size of each node. And we also need to identify the cells because it will need to know, oh, have I been here before? Have I not? Do I have a better approach for this node or not? Because this is a variation of A star for those who are familiar with it. It's a variation that was originally developed for games and for 2D, just for non-player characters to figure out their way around the scenario. So there was some adaptations that were made so it will work in 3D and in this environment. So as I told you, the identification of each shell, and we are only focused on the leaf nodes, which is the ones that the representations here that we are interested in. So I need to come up with identification just for each node that was independent of its size or which layer of the tree he was in. And this was the center of the tree. This is important because it means that the algorithm originally takes into account the corners, but here I'm going for the centers. And this means that actually I am at the same time making a kind of Voronoi map, for those that know it, which is basically a map that assumes that going through the center would be better to stay at a safer distance from the obstacle. Very high level, more or less, is the lines that it talks about. So this identification point is why I had to make this adaptation from here to here. And this will have some implications later on. And so this is just more or less so you can see how the algorithm is thinking. It has this start point and its end point. And this would be how it would see their neighbors in a regular grid. And here we can see the orange points, which is actually the centers of its neighbors. And here they are together so that you can like make the transition smoothly for just the other one, because this doesn't look much like anything. Okay. So the impact of this identification point being in the middle is that here is what the algorithm gets, the start point and the end point. Obviously, it cannot go straight through because of the obstacles. And this is the solution that we get. This is the start point that it gives, and this is the end. So as you can see, they are not exactly the same. And this is the most obvious example because this point is not taking into account what is the octomap, where is its center, or anything like that. It's just like you're a user, you want him to go from this coordinate to that coordinate, you know? But in fact, he will need to adapt from here to here, and this will have implications because you need to make sure that there is no problem in switching from here to here. And I'm pointing this out. This will also have some then implications on the path it takes. So sometimes it goes even further away from the obstacle that it needs to go because of this. So this is, and I want to point out that this outcome is without any post-processing. So this can be an issue on A-star derivative paths that are generated, that they are very jagged and not close. Of course, this is, of any people that know aerodynamics, it's not a very optimal path for a UAV, but at least it's closer to, and that means that we can use it online, have better chance of using it online in real time because there is less processing needed, because the one processing that you are doing is already getting you much closer to the final outcome. Okay. Yeah, and then there is this one other point that I would like to share because it was really surprising for me, and I hope that might be useful for any of you. So I don't know if anybody is familiar with what test-driven development is. One guy, okay. Oh, all right. No, please tell me because I really don't know. Okay, so the idea behind the test-driven development, this is a software development technique. And the idea behind this is that instead you try already to build your final solution, like draw everything, and you have a good idea of where you're going to go and try to get there and then test if it's okay, or sometimes in the middle. The idea is that you first go with the problem and you frame you make a code to show that something is not working. And then you develop according to where you want to go, of course. You don't go starting to do things that doesn't make sense, but according to your development plan, you develop the part of your code that you need to develop so that that test does not fail anymore, okay? And you build your architecture step by step in this manner. And this means that and you always keep these tests, right? And they can be run automatically. And there's even awesome tools from a lot of people that give you statistics on how well it's going. You can integrate it in continuous environment, and you have access to a lot more tools. But another key point is that as you are doing research, sometimes you find about some things that are unexpected, or for whatever reason, it changes a little bit. So to have this unit testing, it enables you to make sure that these problems that you were thinking and you decided which are the preconditions of the question and which are the postconditions that you want to achieve, you can always test them without even having to get into that contest and making sure it still works. So you can just like press a button and make sure that this is still valid. And this can show you a lot of red flags really fast. So this is one side of the why I use this. And also, the other surprising thing that I found out is that just having really small and seemingly very silly examples, you can really probe the search space and find edge conditions to test your code. For example, I used, at first, just because I wanted to know if it was working, just like anything else, I used a unit test that just checked, okay, I have a point A and point B, and I already know that there is a free space between point A and point B. So I already know actually the solution, right? I just want my lazy start implementation to tell me, okay, your first node is your start node, and your end node is your end node. And there's nothing in between, you just can go straight, okay? So finally I got this to work. Yeah, I have to admit, not on the first try, but eventually it worked. And I was very happy. And then I thought, okay, so I know it works for this two coordinates, but I can actually verify for coordinates that I don't know which they are beforehand if it's the same test. So I could actually automate everything so that for all the search space, you can test this thing and it works. And this, I cannot even begin to tell you how many edge cases I found out just doing this. And like, just pause for a minute. This means that you can go to your simulation environment, collect your data cloud for whatever situation you may be. So maybe you're in marine, then you go to some disaster emergency scenario. You can change your scenario, whatever you want, or whatever point in the exploration phase you are, more known cells, less known cells, anything. And then you take a snapshot of your octomap tree, okay? And then you can feed this into this unit testing that you have, and you can make sure that for all the space, every single space, it works when it's a free line. And I know that maybe for people that are not so much developers and have not tried to do any challenges or tests or anything like this might seem, you might be thinking, okay, isn't like the way it's supposed to work and you're already working every time? No, it's not. Many times the only option that there is that you do individual tests. And you do individual tests in individual scenarios, and then you were in this context of this bug that was happening in this precise moment in time, but then you're not anymore, and it changes, and everything changes, and you have no actual way to measure your progress with numbers, actually. And you can also ask, like, how well am I doing in 1 meter, and how well I am doing 10 meters, or whichever you want. And this also allowed me to check in the different cases that can happen, how well was this new approach doing as opposed to the just using the regular grid, because of course the calculations for the data footprint storage is easy to make, more or less, but the octo map is not going to construct itself in the same way for every scenario. You have no way of actually quantifying, for this scenario it will take this amount of nodes. There is no way to do it because it varies a lot. If you start taking into account errors, even more. So this actually allowed me to check that for this amount of situations, it did took less than half of iterations less than the regular grid. So this is how much better I did, and this is how much better it did when it was half or more as the one it would take in the regular grid. But also, it warned me that, okay, this is nice and everything, but you also have some situations when it takes more. Even if it's not a lot more, just a little bit more, but you still have those situations. And you can see that it's more or less consistent if it's short distances and if it's long distances. Okay. Yeah, I don't know if you can see this, but like this was tested in 1,962 cases, and this was in 320 cases. Okay, so obviously in future work I need to grab my simulations and my unit testing and make it work in the real world and to make sure it works in the real world. Also, I'm very interested in adding some more heuristics into the choosing of the frontier cells, because you get like a bunch of frontier cells and then you need to know which order you're going to explore them in. Yeah, and yeah, putting all of these nodes together. Yeah, that's all from my side. Any questions?